All right, welcome to Module 9, where we are diving into hypothesis testing. In this chapter, we will start to analyze our assumptions and develop this framework of hypothesis testing for how we can understand this population parameter using our estimates of our statistics and essentially wrapping all the different concepts we've been talking about with confidence intervals and pretty much everything leading up to the class. This is a big turning point where we'll actually start to be able to test our assumptions and have some type of frame of reference to say, with what certainty are we that this assumption is correct? So we'll be tying together aspects of probability, of confidence intervals, and bringing it into this concept of hypothesis testing. So just to start us off, this is a little cartoon from XKCD, which has a lot of great statistics, data science related cartoons. So I definitely would recommend checking them out. But I liked this cartoon.
Can't see the screen.
Pardon?
I can't see the screen.
Oh,
it says you started sharing your screen, but for some reason it's not popping up.
I'm very glad you're here to alert me. Let's try one more time.
There we go.
Okay, beautiful. And the only other thing you missed was just our introduction slide, which just is saying, how do we test a theory? Thank you very much for catching me on that. This is the cartoon, and it's looking into this new theory that one of these little cartoon characters has about jelly beans causing acne. And scientists are going to go investigate this. And this is something where they have this p-score. I don't know if anyone's familiar with a concept like p-hacking, is how you use this p-score of significance to say that there's a link between jelly beans and acne. So that this cartoon is just going to introduce some of these concepts. We'll talk about p-values and what that means. But pretty much this just goes through an iterative approach of these two scientists really trying to figure out if jelly beans link to acne and using this p-value to validate that there is some type of connection in their different experiments. So this is just to introduce how, bringing it all back to chapter 1, when we talked about scientific theory, and you need to be able to have it falsifiable to actually be able to prove that your theory is true. So this cartoon just introduces us to this concept of a hypothesis. You think jelly beans cause acne. You need to start to develop a hypothesis to falsify that claim. So you would have an alternative hypothesis, and we would want to determine at what significance threshold would we actually be able to say it's true that jelly beans cause acne. And we'll use statistics to prove these hypotheses. So why this all matters, this is how we test our theories, make decisions about real life problems, and really structure everything we've covered so far as it relates to probability and statistics in this framework of a hypothesis. So it's very important we get this language right as we're starting to use this framework of hypothesis testing. And we need to think about it as everything is falsifiable. So we need to think about it and define it in that way. And pretty much in this case for this jelly bean, if that's your hypothesis that jelly beans cause acne, we need to start with saying that jelly beans don't cause acne and use our experiments to prove the alternative that jelly beans do cause acne. So the way to think about this, it's almost like when you're thinking about our freedom of being innocent until proven guilty, we should think of this null hypothesis as there is no difference in jelly beans causing acne, or thinking you're innocent until you're proven guilty. And the verdict is based on limited evidence. And that's the whole purpose of having a court decision, to bring new evidence to say why the person on trial should be considered guilty, or this alternative hypothesis of jelly beans causing acne. So essentially everything we'll be doing is in order to create new evidence to prove against this null hypothesis. So thinking about it just as a way to remember this framework, the null hypothesis is there is no difference between jelly beans causing acne, and those two scientists needed to come up with experiments in order to prove that there actually was a difference. And in this case, you could think of this rule as innocent until proven guilty. And we are, as statisticians, or if we're on trial, trying to find evidence to prove the alternative hypothesis, that there is enough evidence to conclude that this individual is not innocent. And the way this translates back into what we'll be doing is how we will either reject or fail to reject this null hypothesis. So if we have enough evidence, to say that this person on trial is guilty, we would be able to actually reject the null hypothesis and say that this person is not innocent, or we have enough evidence that jelly beans cause acne to reject the null hypothesis, saying that jelly beans have no relationship with acne. The other way we would go through this, if there wasn't evidence, if those two scientists found that through all their trials that there was no relationship to jelly beans and acne, we would say we would fail to reject the null hypothesis, and saying that there's not enough evidence to suggest that this accused person is not innocent. So it means that they are innocent. So these are essentially the two steps. So as we walk through some examples, what you see at the bottom, like this is the language that we'll be using of saying we either do not reject the null hypothesis or we reject the null hypothesis. And essentially that aligns with the two different options of saying either there was no relationship between jelly beans and acne, or there is one and we found evidence to prove it.
So just to clarify, the null is the hypothesis that you come up with?
And what do you mean by what you come up with?
Like when I say jelly beans cause acne, that's the null or no?
Yeah, that's an excellent question. And that's really where we'll have to start from, where pretty much you just have a theory, you apply that theory in this framework. So you are creating both hypotheses, the null, it's usually referred to like H naught with that H with the 0, and the alternative with H and the A. Mm-hmm. And so your theory, you need to translate that into both the null hypothesis and the alternative. So your hypothesis is that jelly beans cause acne. That's actually the alternative hypothesis. You would need to also disclose what the null hypothesis is, which is saying that jelly beans do not have any relationship with acne.
Okay.
So to answer your question specifically, you have to come up with both.
All right, that makes sense. Because you want to make sure, because if you're wrong, you can still put out the whole theory and everything like that in the other direction.
And that's where using reproducible research and this significance value of this P-score, which we'll get into, is how you would say, I have this evidence to prove that there is a relationship. But we always need to start with this falsifiable sense of like, there is no relationship, and we build from there. And that will be consistent with every hypothesis test we use. Always you start with this state of innocent until proven guilty, and we are just finding evidence to try to make this, this accused person, guilty in a sense. Does that make sense?
Yes.
Awesome. So yeah, once that framework makes kind of intuitive sense as we start to go through examples, it'll show how everything else we've kind of worked up to at this point aligns with this framework, where we'll be looking into like the tails and the area under the curve. But I just wanted to bring in this quote because really what we're getting into now is the basis of a lot of scientific theory and how statistics are used to really understand the world around us. So I liked this quote from Enrico Fermi, who's an Italian physicist and the creator of the world's first nuclear reactor. And one of a physicist who excels both in theoretical physics and experimental physics. So I like this quote saying there are two possible outcomes. If the result confirms the hypothesis, then you've made a measurement. If the result is contrary to the hypothesis, then you've made a discovery. So this kind of just tees up how research can also be biased to try to find some type of discovery, because that's more publishable than saying, there was no relationship between jelly beans and acne. So this kind of just introduces this whole paradigm of research around hypothesis testing, and kind of just says that there is incentive to try to find discovery if you're a researcher, but this whole process helps to confirm our understanding and measurements of how things work. And really this talks about how we can actually mathematically test these different theories using statistics. So this null hypothesis significance testing framework requires us to break it down into these very distinct bins of null hypothesis, alternative hypothesis, and we can start to have these different testing frameworks. So we have a two-tailed test, a right-tailed test, and a left-tailed test, and all these different tails align with our area under the curve. And we'll start to use statistics to prove either these two different groups are the same. Let me walk back a little bit more with just an example, thinking back to when we were learning about Gossett and being the master brewer when the t-test was being developed, where he was trying to prove that different crop yields would have varying properties based off of, let's say, for example, fertilizer that's used in one pool of samples compared to the other. If he wanted to come up with this conclusion that, let's say, the quality of hops was better in group A compared to group B because of whatever experiment he was running, let's say using fertilizer, the null hypothesis would actually be that there should be no difference in, let's just call it like the height of the hops between these two groups, with one having fertilizer and the other not. That's this null hypothesis saying that there is no relationship between using fertilizer and hops height. And so between group A and group B, we would expect the hops height to be the same. So that would represent this average height, or mu, of group A to be equal to group B. And that would be this null hypothesis. But let's say through experiments, we find that there is a difference in the average height in these two samples. That would start to gather new evidence to suggest that there is a difference between hops in group A and group B relating to this fertilizer usage. And depending on how extreme that difference is, we would be able to gather with more certainty that we should actually reject this null hypothesis and say, hey, there is a relationship between adding fertilizer and your hops height at this degree of significance. And when I say to this degree of significance, let's just say the heights differed by barely an inch. Is this enough evidence to actually say that there is a relationship between adding fertilizer to your hops and the height or the quality of the hops? That might kind of just be due to random chance. So we need to be able to use statistics and this framework of probability of what's the probability of seeing a value as extreme as, let's say there was, a 20-foot difference, just to be very extreme in this regard. Let's say the hops that had fertilizer grew 20 feet higher. That would be very apparent to say, wow, we found a new discovery. This is very significant. And we could state that there is a relationship between fertilizer and the hops quality. So that's really what this whole slide is talking about, how we would test these things. And the right hand tail and the left hand tail is using the area under the curve to say that what's the probability of seeing a value higher than this or lower than this, and thinking about with the two-tailed test of the mean equaling this value, this is now accounting for how far from the mean being 0, like the mean difference, for us to say that this was significant. So we would be able to use this to then reject the null hypothesis if we find evidence that is extreme enough to fall outside of our confidence intervals. So thinking back to the last class when we were talking about different error margins, to say over 95% would be something that when we're trying to predict the probability of our estimate being within the interval, this is using that same framework to say, what's the probability that this is outside of that expected range, which would give us evidence to say, hey, these means are different, these groups are different. There is some type of significance difference in these values. And we can say with probability, how much of a difference is it compared to the expected interval where you would see. So thinking back to that example with the hops, if there is no difference between the means in two different groups, you would expect, let's just look at this last distribution, you'd expect the mean height of the hops to be within this interval of, let's say for 90% confidence would be 2 standard deviations from the mean. We would expect both of those mean heights to be somewhere within that interval. But let's say one was now 20 feet higher, we would see even, if it's 20 feet lower in the other group, I'm just bringing that up because we're talking about two tails. We know that that value of the mean difference is much greater. And that gives us evidence to say we should reject the null hypothesis. So next we'll run through some examples to illustrate this concept, but I want it to be clear that we are using this area under the curve as a way to measure the probability of seeing a value as extreme as the value that we observe when we start to test the differences in these hypotheses. Any questions?
Yeah, so for the not the null hypothesis, but the regular one, it looks similar except for it would be greater than or equal to on
The alternative hypothesis?
Yes. Because that was the one you just showed on the chart, that was the null.
This one, these are all the alternative hypotheses.
Got it. Okay. And then the HA, that's for alternative, obviously.
Exactly. So that's why I was referring to H naught as the null and HA as the alternative.
Okay.
And this gets even into some of like our Boolean aspects that we discussed. If we wanted to make sure that a value is greater than or equal to, we want this to be mutually exclusive. So everything that's not greater than or equal to would be in the alternative. For example, just this left-tailed test.
Okay.
Any other questions just regarding the split and the difference and just why it's important that they're mutually exclusive from each other?
I'm just looking at the thing right now, the little chart you have in front of me, just to make sure I understand it. So whenever it's a two-tailed test, they both have to be either equal or not equal to for either one. And then once you get into the right and left, that's when it gets a little more different. So whenever it's a null, it's equal. It can be equal in any of the aspects. But when it's alternative, it can't be. One is greater than the other, or they don't equal at all.
I think once we go through some examples, it'll help when we would use these different tests. I think for now, as long as it intuitively makes sense that the null hypothesis is essentially saying that there is no relationship. So for example, like the means would be equal to each other, would be this null hypothesis. And then if we did find something that is evidence to suggest that the means aren't the same, that would go as evidence for this alternative hypothesis.
Oh yeah, so because you wouldn't know until you do the test.
Exactly. So we kind of
Got it.
want to always think, like we want to just establish our naivety. Like we don't know how things work as scientists. We need evidence to prove it. We need to first go to this default of there is no relationship, this person is innocent, and use our evidence to suggest something is not, we need evidence to prove against this innocence, or to prove that there is a relationship.
All right, I get it.
Awesome. And then with the right-tailed and left-tailed, this is just different questions that we can start to answer with this. So if we're not just comparing the means between two groups, but if we wanted to say, for example, group A is more likely than group B to have higher growth, we can start to use the right-tailed and left-tailed tests. So these are all getting at a same concept, just different ways to answer different questions.
Cool.
Awesome. And definitely keep asking questions if once we go through some of these examples and there's still more clarity to be had. Because this is the same steps we'll take, and we'll apply it to different examples. So this kind of answers the question, how do we know when to use a right-tailed or left-tailed or two-tailed test? It depends on the question that we're trying to answer. And that is why the first step when we're going through this null hypothesis significance testing framework, where these are the 3 steps we will take. So first, we want to identify what's the relevant population parameter of interest. Are we looking at the mean, standard deviation? Are we looking we can apply this to correlation as well. So first, depending on, what's the question we're trying to answer, we would establish what are the relevant parameters of interest that we're trying to measure using statistics. Second, we'll determine whether this is a one or two-tailed test based off of, our experiments. And 3, we establish a claim, and our claim is the different null and alternative hypothesis. So thinking back to those 2 scientists trying to see if jelly beans cause acne, the claim would be jelly beans have no relationship to acne as the null hypothesis. And then the alternative of, essentially what they're trying to prove is saying that jelly beans do cause acne. And they would establish the population parameter. In that case, they want to know, the mean number of, pimples, for example, if they're trying to measure this in an experiment. So this is the framework we'll use. Let's walk through an example here where you are the head of a marketing department and you're predicting that the average spending will be $76.50 per customer as a result of this new pricing promotion. So let's start to frame this. Let's just say this is like your claim, because you want to suggest that this new pricing promotion will result in more spending per customer. So validating this assumption, we are using the average. So this is our population parameter. We want to know the means, and we want to determine if the population mean differs from the expected value. So the way we would frame this with our null and alternative is to say that this is what is expected to happen of this null hypothesis. And this alternative is saying that there will be a difference as a result of this pricing promotion. So we can now start to test this. So let's just go through this is just breaking down how we use our relevant population parameter and establish this framework around it by saying either it will equal this or it will not equal this. So let's go through another example. Let's say you are at a construction site and want to be able to allocate different risk mitigation strategies, and you want to make sure that you will have this new program introduce more risks being reported as a result of this new initiative. So the claims that the mean report will be more than 3 high-risk projects reported as a result of this. So the way we use our new framework of null hypothesis testing, we need to say that if we fail to reject the null hypothesis, we cannot support the claim that we only see 3 high-risk tickets. So this essentially is saying without this new initiative that we would expect to see less than or equal to 3 high-risk tickets being reported. But if this program did have some type of effect, that we would expect to see more than 3 high-risk tickets events reported as a result of this new safety management program being introduced.
So if we have like 2 high-risk tickets, then it's null. If we have 8, then it's a alternative.
Yeah, I like the way you're thinking. I think the only thing I would do to adjust that a little bit is that it's not so cut and dry like that, just saying either, it's 2, so therefore we, fail to reject the null hypothesis. I just wanted to change that framing of saying like this was evidence that was found that we do not have enough evidence to reject to reject the null hypothesis and have this alternative hypothesis. So let's say there was only 2 tickets. We would say there's not enough evidence to reject the null hypothesis because, we didn't find enough evidence. But for 8 tickets, you can start to say, this is evidence to reject the null hypothesis and go with this alternative hypothesis. But to what degree is it significant? Is 8 tickets significant enough? That's where we get to this p-value. But yes, you're exactly what you're thinking is right. I think it's just how we communicate that is really important.
Okay. Just wanted to make sure like I was like on the right page kind of.
Yes, exactly. So, and just in this last example, we want this to say on average, they spend $76.50. And as a result of this new pricing program, as long as they spend either, maybe this new promotion makes people actually spend less money or more money. This is developing that framework to say, now we can start to test. And after this new program, let's say we take like a sample every month to see, is there evidence to support that this new pricing promotion changed the average spending?
Okay.
So I just bring that up because really right now, this is just establishing how we take a claim and translate it into something that's testable and where we can start to have evidence to either support our claim or support the null hypothesis. So let's go through one more example because these are just covering the 3 bases of when it's 2-tailed, which was that first one with the mean, the last one was 1-tailed, and now let's do the other side of the tail. For this example, let's say you are testing, this is now the population proportion, where we want to say at least 85% of shipments are energy efficient. Let's say, you're in charge of logistics and there's new ESG requirements where you need to make sure that you are having your shipments be energy efficient. We want to now test that 85% of all your shipments are energy efficient. So let's see if the different efficiency levels have decreased due to new supply chain risks. So the way we would frame this is essentially saying that there is a decrease in energy efficiency as this alternative one, to say, so this null hypothesis of saying at least 85% or more are energy efficient, and we want to actually now test if things have decreased due to supply chain risks, and that would be our alternative. So we would now need to take a sample and see if our shipping efficiency is either 85 or above. Everything is still in this default of our null hypothesis, but if we find evidence to support that energy efficiency levels have dropped due to some new exogenous risk of supply chain, we would now have evidence to support this alternative hypothesis. So this is the different examples that would relate to how we would use the area under the curve and which side of the tails we would need to see a value fall into to say with certainty if we should accept our theory or reject it. Any questions on this last one?
No.
Okay, perfect. So just at this point, I want to review where we're at. We've just walked through our framework of how we set up null hypothesis testing. Depending on the question we're trying to answer, we use these different tailed tests. So in that first one, we're actually using that two-tailed test of saying that the average spending is different than what it usually is because of results of our new promotional program. In the second example, we were talking about our different safety program, and we want to now say it'll be more than we would expect to see. That would be this right tail test. And then that last example where we said that the energy efficiencies would now be below a value, we would use that left-tailed test. So this gets back to chapter 6 when we were doing this continuous interval testing. So even just knowing which side of the tail you're trying to calculate for would be technically solved using either you subtract it from the cumulative distribution or you use the cumulative distribution value to get that probability. And don't worry if what I just said maybe doesn't resonate. Once we get to the demo, I'll show you how to actually calculate it. But we really have all the tools to calculate these things. It's now just applying it to this new framework of hypothesis testing. And next, I want to get into kind of like what happens once we have this testing framework. And even just when we were talking about if we found that only 2 tickets were reported after that new safety program, should we say, oh, this safety program was a bust and it didn't actually help us report more high-risk tickets? This is how we need to start thinking about, did we make an error in our hypothesis testing? Because this hypothesis test is still based on limited sample information. We're bound to make errors. Ideally, we would want to be able to reject the null hypothesis when indeed the null hypothesis is false, and then not reject the null hypothesis when the null hypothesis is true. However, we may end up rejecting or not rejecting the null hypothesis erroneously. due to either random chance, or perhaps we're not using the types of experiments that were really needed to prove our theory. But this whole paradigm, let's think about it as we either get it right when it was wrong, or we get it wrong when it was actually right. So in other words, sometimes we reject the null hypothesis when we should not, or we do not reject the null hypothesis when we actually should. So this would be a type 1 and type 2 error by definition, where type 1 is when we reject the null hypothesis when the null hypothesis was actually true. And the type 2 is the opposite, where we fail to reject the null hypothesis when the null hypothesis is false. And this should be similar to the last class when we were talking about this confusion matrix of when we make the correct decision and predict that, that there is no relationship. I shouldn't use the word predict, but let's say accept this null hypothesis that there is no relationship between using fertilizer and the hops quality. But what if we make that judgment based off the sample? We only found like an inch difference, but actually in reality, there was some type of significance around fertilizer, and we failed to reject the null hypothesis. This would be a type 2 error, where the alternative hypothesis actually was true. There was some type of relationship. And the opposite, using that same example of if we rejected the null hypothesis, where we said that there is a relationship when we found that 20-foot difference. But what if maybe there was something else in the soil and it wasn't really the fertilizer, maybe just this area had more sunlight compared to the shady area, where we say, hey, there's this crazy new discovery we found. This would be a type 1 error, where we have this almost like a false positive, where we rejected this null hypothesis to accept the alternative. Meanwhile, there was no relationship between fertilizer and the height. So thinking about this, thinking in this framework of false positives, false negative. Actually, I want to show this chart instead. Kind of just thinking of this as a binary decision, thinking of this as like a coin toss model. Let's say you're trying to predict if the coin will land on heads or tails. I just want us to think about this as you predicted heads and it was heads. That would be a true positive. And the other side of that is you predict tails and it was tails. And we could think of these type 1 and type 2 errors as these red boxes for when you predicted heads and it landed on tails, or you predicted tails and it landed on heads. So don't worry about too much of the other details here. I just want us to start thinking how this actually has a lot of applications, specifically in data science and machine learning. When you're making predictions, we use these types of performance metrics to actually gain trust and credibility in a model that we're creating, when we could say, on average, how often do we get it right out of all the times where we predicted something to happen, compared to how many times do we even predict something to happen. So bringing this back just to our hypothesis testing, this is when we say that there is a relationship and there actually was one, compared to when we say that there was no relationship when there actually was a relationship. Any questions on this? But really, this is the most important slide. I just brought in some of that other context to bring this back into real life, and kind of, I work with these things in my job when we are developing models and we need to validate our performance and communicate the probability of seeing these type 1 and type 2 errors.
Can you go over this part one more time, please?
Yes, for sure. Because this one is important and will be covered in the homework as well. Really just knowing these definitions is the most important part. And the reason we use this is because we need to state when we get it wrong. And these are the two different ways we can get it wrong. So thinking about the different things that can happen, even let's work backwards and let's use that example of is the hops example helpful to stick with in this case? Would you like me to walk through that one again?
That's fine.
Okay, so in that case, our null hypothesis would be that there is no relationship between fertilizer and the hops height that was used in, A/B testing. So sample A had the fertilizer, sample B did not. Our null hypothesis would be that there is no relationship between fertilizer and plant height. So if that is the case, and let's say we now wait a few months, we collect our hops and there was no difference, we would fail to reject the null hypothesis, which is just the scientific way of saying like we accept the null hypothesis, but we need to be consistent where we fail to reject the null hypothesis, which pretty much translates to we didn't find evidence to reject this thing, so we accept it. So that would be this true state of the null hypothesis is true. We made a correct decision, that there really was no relationship between this new fertilizer. Where the type 2 error comes in is if there actually was a difference from the fertilizer, but for some reason our experiment didn't result in a value that showed a significant difference in the mean height, and we just didn't capture it. So that would be this type 2 error where we missed it. So that would be this false negative where we said, hey, there's no relationship when there actually was one. So even, I don't know, hopefully this doesn't confuse more, but if this was back to a test of, let's say for testing an illness, this would say, hey, you're actually healthy. There's no issue here when you did have an illness. So this would be like a test not finding that you had an illness and saying you're good to go. Meanwhile, you could be potentially like spreading the illness. So this is a false negative where you didn't capture that there is a relationship between, fertilizer and the plant height, or in the instance of a test of seeing if you had the illness, it failed to see that you had an illness, said you're fine. And this could actually be more dangerous than on the opposite if we say that there is a relationship between the fertilizer and the plant when there actually isn't one. So that would be this type 1 error, or like a false positive. So we said that, hey, you do have this illness when you actually didn't. So maybe you would go and get tested again and find out, oh, that first test was wrong. So that's this type 1 error or a false positive. So back to the case around the plants. Let's say you do state that the fertilizer caused the mean to be significantly different, but meanwhile, it was the trees or something else that caused the difference, and the fertilizer actually really wasn't the driver. So you have this false positive, and that would be this type 1 error.
Okay, that makes sense now.
Anything else I can help clarify?
Actually, no, you did perfect.
It's here. All right. So let's move forward. This just further demonstrates what we just talked about. And actually I use the example that I just brought up, where our null hypothesis would be a person is free of a particular disease, they're healthy, where we need to find evidence, let's say through like a test that looks at the antibody levels, or, I definitely am not very well versed at all in medical subject matters, but let's just say, for example, we found evidence through a test to say that this person is likely to have the disease. That would be our alternative. So we need to collect evidence to reject this null hypothesis and say this person is free of a disease in order for us to suggest that this person actually had the disease. So this would be in the textbook where you can read through this and think through what we just read through of these type 2 and type 1 errors of false negative or a false positive. And again, depending on the context, there are different consequences. So as a data scientist, when I'm developing a model, I need to understand the business context around kind of cost of making a type 1 or a type 2 error. And of course, you want to get it right as much as you can, but thinking depending on the consequence, it might be better to have more false positives in order to never have that instance where you're sending someone out thinking that they're healthy when they actually are not healthy. So depending on the consequence, you might actually want to weigh your significance towards one option or the other, to either like say, hey, even though it wasn't super extreme, like we only found a few, antibodies, we should actually still say, hey, this is enough evidence to say that you're not free of the particular disease and you should go get tested again. So I just want to bring this back into the context that it's never really cut and dry. It's more so this evidence supports this claim, and to what degree does it support it? Is it extreme enough to say, this would only happen because of a relationship and not just due to pure random chance? And, what's the probability of that happening? So there's this gentle balance between type 1 and type 2 errors. And if this was bringing back to the real world, you should really always ask yourself, what is the cost of a false positive? If we miss to catch this, the cost would be X. And if we incorrectly catch this, what's the cost? So back to this disease example, maybe the cost is for another test, and that cost is much lower than the cost of saying this person is healthy when they actually are not, and they're spreading this disease. So it's always good to define some of these different assumptions and the cost of your assumption whenever you're applying this to the real world. And as we keep building onto this, we're essentially just repeating ourselves at this point, but now framing it in this way of this null hypothesis testing, when we are considering this probability of getting data at least as extreme as the data you observed if the null hypothesis is true. This is just the pure definition of that p-value, and that's what we're about to get into next. So even just from that first example of the cartoon where you had those two scientists saying a p-value of 0.05, that is saying the probability of seeing acne levels in their experiment to that degree as extreme as you observed if the null hypothesis is true, we can say that there was a relationship. So this is just saying we want to make sure that this discrepancy is not explained by chance. And we'll walk through this more next, but this is all just showing that area under the curve and saying what's the probability of getting a value at least as extreme as the value we observed if the null hypothesis is true. So just thinking back to the area under the curve, if something is pretty much right near the two standard deviations and not in the tails, we could say, hey, like there isn't anything rare about this. So there isn't any relationship between acne and jelly beans. But because there was a relationship we found where this sample of, let's say, 300 people who ate jelly beans every day saw a significantly less number of, pimples on their face, we could say the probability of this value is extreme enough to support rejecting the null hypothesis. So we use this data to inform the probability of a value at least as extreme as the value we observed if the null hypothesis was true, which the null hypothesis being true would mean we shouldn't have expected any difference in the number of pimples on your face based off of the consumption of jelly beans. But if we do, it needs to be extreme enough to state that there is evidence to reject the null hypothesis. And this is this p-value. So we'll get into that. This is just talking about how we use that z-score again to define what would be the expected probability of seeing a value. And this shouldn't be new because this is the same exact z-value we were just talking about, where we have the use of the number of observations as n. This was like the standard, the error when we were talking about in the last class when we had confidence intervals. So we use the same as a test statistic for our hypothesis testing, where we have this value of how many standard deviations from the mean would we expect to see. And this continues to depend on our data being normally distributed as an assumption. So all of these different frameworks depend on normally distributed data because we are leveraging the symmetry in the tails again. And this all relates back to chapter 6 when we learned about the normal curve. So let's go through an example of how we would evaluate this. So let's say you're a market analyst and you want to establish that the mean age for individuals who are rejected from a credit card application, that the age is less than 25. So it is assumed that the card application age is normally distributed with a known population standard deviation of 10 years. So let's have a random sample of different applicants and that it produced an average age of 25. These would be our null and alternative hypothesis to say that the default is that the average age of individuals who get rejected is actually the opposite of what we're trying to prove, to say just this is the default. Hey, there is no necessarily like significant difference for anyone who's less than this age. We're just saying that the mean value would be expected to be over 25. And this market analyst is curious if the mean age is actually different than this. So we would, and actually specifically less than 25. So this is the framework we would use, where we would collect a random sample of applicants and see what the average age is of the different applicants if they get rejected. But now let's talk about this p-value. And again, this is the likelihood of obtaining a sample mean that is at least as extreme as the one derived from the given sample, under the assumption that the null hypothesis is true. So now bringing this to our area under the curve, we have this p-value to express this probability of obtaining a sample mean that is extreme enough to be considered significant. So we use, similar to last class when we had these confidence intervals of 90, 95, and 99, we'll tend to see a similar breakdown because that's kind of where things in the industry is just defined at 0.05 significance. That would be over 95%. So let's say if you had out of 100 people and you had a 95% confidence interval, we can start to calculate the probability of seeing a value at least as extreme as that is very rare. So if we were going to 99% confidence interval, that would result in only 1 out of 100 seeing this value due to chance. And therefore, if we do see a value extremely far from the mean, then this is enough evidence to prove that there is a relationship and we should reject the null hypothesis. So we use this significance threshold to define. We should define this before we even test anything. Just as scientists, we should say, like, what is enough significance for us to make our claim testable? You know, so different needs have different statistical significances. So if something needs to be really extreme, we would have 99% confidence. But if something like the jelly beans, they were using a 95% statistical significance, sometimes it's thought of as like 0.05 is enough to say it's significant enough, which is this 95% statistical significance threshold. So kind of depending on how significant it needs to be, you would move this statistical significance threshold further to the right, or you needed this value to be even more extreme. So kind of just thinking about this in the other sense, if we didn't really care about significance at all, we would see a value in this area under the curve that's very close to the null hypothesis. And essentially that would just be kind of due to random chance. We could have a little bit, this would be, for example, with the plant just being an inch higher in the A/B testing. You know, this isn't anything extreme enough to reject the null hypothesis that there is no relationship, but the value like 20 feet higher in the mean is extreme enough. And that actually would probably be so far away from the mean that it would pass the 95% statistical significance threshold, the 99% statistical significance threshold. So therefore we could say with this type of certainty of, we saw this value that's super extreme and it is so far away from the mean that it passed our statistical significance threshold of 95%. So I threw a lot at you there. What's most important there is to say, before you even conduct the test, you should establish this statistical significance threshold that you are okay with. So sometimes this 95% is good enough, usually for research purposes. But that is very questionable. And there's a lot more to it than just saying, hey, my p-value is over this value, therefore, you know, this is accepted new discovery. And that's why reproducible research is so important. That's why making sure that there's enough samples to prove that this wasn't just by random chance. So I'd encourage people to look into like p-hacking, because sometimes you can really change the experiment in order to get a value that is statistically significant, but essentially meaningless in the real world because it was just due to how you manipulated your samples. But that's a bit of an aside. But thinking about this p-value in its most essential aspect is we observed a value so extreme that it passed our threshold of saying, hey, we would only see a value this extreme because there's something else going on here. And it's not just, you know, due to chance. Does that all make sense? Because it really, this is bringing back to distribution. This is bringing back to probability and bringing it and applying it into this new sense of how we actually test our theories. Because again, if we were just looking at heights of plants, we would expect most values to fall near the mean. And only if there's something afoot, we would see the value very far away from the expected mean.
So it's just like a combination of like most of the stuff we learned into one.
Yes, exactly.
I understand it somewhat, but I feel like once I see it like in action, then I'll probably start putting it together more.
Okay, perfect. But as long as those threads are coming together of using area under the curve, that represents the probability of seeing a value and thinking about, standard deviations from the mean. And this statistical significance test is just saying this value is more than, 2 standard deviations from the mean or 3. And if it's further away from the mean or in these tails, then it's an extreme value that would suggest something's going on.
Yeah, I got that part.
Okay, beautiful. But yeah, I agree. Once we have more application and examples, then more questions might be needed. But for now, that's good to hear. And we will move forward with some examples. This just ties it back together of what I mentioned is really important, that you should set this significance threshold before you even start implementing your hypothesis test. Because let's say, for example, you get a significance value that is, beats the 90, but doesn't beat the 95. But then you see it and you say, okay, so let's set the significance at 90. That defeats the purpose of scientifically testing something. So before you even test it, you should define what is your threshold. So that way you can test against it. And depending again on the different use case, we should use these significance levels. And these are communicated in that alpha from what we learned in the last class. And this is just that area under the curve minus from 100%. So this would translate to, 99%, 95, or 90. We use the alpha in the same exact way. And we reject the null hypothesis if this p-value is less than the value of alpha we see. And we do not reject the null hypothesis if the p-value is greater than the alpha we see. And this is really where it all comes together with this area under the curve. If we see a p-value that is less than our threshold, then it is further along in the curve. It's more in the extreme side of the tail. But if our value is greater than this significance threshold, then it's within this area of the curve and it's not as extreme as that value. And therefore, we failed to reject the null hypothesis, saying that this point of evidence was not extreme enough to reject the null hypothesis. So therefore, we do not reject the null hypothesis, or you could say we fail to reject the null hypothesis because the probability of seeing this value was pretty common and it wasn't extreme enough because it fell under this area of the curve and not in this dark blue side for it to pass our statistical significance level.
Just to make it like in layman terms, I guess. So basically, like back to the with the jelly beans with the acne. If someone had a jelly bean and they only came up with like 1 or 2 pimples, that's not so bad. You can't really connect that to them jelly beans being the cause. But if the person had like 15 pimples after having 2 jelly beans, then they would be in the extreme and you can link it.
Yeah, exactly. Just there, I think there's some caveats to the way you framed that, because I think if we were to bring that to an experiment, we might not want to just say like how many pimples on the face being like, and I think I use that example. If we were using this in an experiment, it would need to be a significant sample size. So let's just say out of like 100 people, we'd probably want to make this like a binary of, did you see an improvement in acne? Yes or no? So we would say out of 100 people, if 25% of them saw an improvement in their acne as a result of having jelly beans, is that 25% different than, let's say you would have to have a control group who didn't have jelly beans, and let's say, only 10% of that group saw an improvement in their acne. Is this 25% compared to 10% significant enough to say that jelly beans actually cause acne?
Got it.
But what you were thinking was correct. I think just bringing it back into context of how we would test this is actually really important, because it's using that probability of out of 100 people in this control versus the group that actually had jelly beans. And now we have the difference in the proportions. And now we want to know, is this difference extreme enough to state that there is a relationship?
I got you.
Perfect. And these are really abstract concepts. So I think, just talking through it more, bringing it to examples, because this is all we'll be covering in this chapter is really just testing these hypotheses and walking through some examples of all the different questions that might be asked. So this brings it into the different scenarios that we might come across when we have either a right-tailed, left-tailed, or the two-tailed tests. And the way you know which one to use is dependent on the question itself. So next we'll go through a demo where we walk through some examples of the hypothesis testing. Let me open that up. So here is the demo we have. I will load in my packages. And I just wanted to bring this up just because this package here is important for importing new data from this stats models package. So if anyone is interested in using the case study, I would recommend just checking out all the different data sets that this package provides. It's the same ones if you've worked in RStudio. They have a lot of other data sets, but that is a resource. So, but in order to get the data, you have to have the package here and import that. And so some of these other ones that we have, we've already looked at for plotting, for doing any type of statistics work. And we've used some of these others before, but I just wanted to repeat this because this is new from last time. So we're going to play around with this credit history of credit cards. And this relates back to the example we had in class. So I just grabbed this from the website. Let's just look at what it looks like, where we have, and there's more information. If you actually click on this, it would bring you to the website and tell you more about what's in it and all the different factors that exists and where it's from. Because it's always kind of important to think about what is the bias in the data that we're using. If we were to apply this in a real setting, not just for demonstration purposes. So pretty much this shows the average age, their income, and other types of features that might be interesting. But for now, we're just looking at the age and we're looking at if they were accepted or rejected. And I believe this is, real data. So it could be kind of interesting to see what happens. So as we talked about in class, this is how we would frame the problem. So essentially, we are looking to test our new theory that this market analyst is hypothesizing to say that people who get rejected from credit cards are actually less than 25 years in age. In order to test this, we break it down into this null and alternative, where the null would be essentially the default of saying that there is no relationship to being less than 25 and the probability of being rejected. This is our default of saying, no jelly beans causing acne, the person is innocent. I'm just bringing back all the examples we've covered so far. And our alternative is proving the opposite, to say that we want to find evidence from this data set to see if the average age of folks who get rejected is less than 25. And if it is, we would find evidence to say, hey, this market analyst has a new discovery in a sense. But in order to have enough evidence to see a value at least as extreme, it could just be due to random chance that this sample had an average age that's less than 25. So, but for us, let's just say at a significance level of 0.05, or this would also translate to 95% of the area under the curve, and only looking into the right tail in this case to see a value. Actually, the left tail would be less than, but let's walk through. We'll visualize what this looks like, but pretty much we're trying to define that the average age is less than this value, because that would be evidence to reject the null hypothesis if we see a value. So in the homework, I would just think through, what would I need to see in order to either prove this claim or show if there's not enough evidence to support the claim. So we define the average being 25, and we have our standard deviation. But in this case, I'm going to plot this so we can just get a better sense of, our population of what we are working with. So if this was on an exam, I would expect to see, and in homework, I'd expect to see a little caption below about this distribution. So we can say, it looks normally distributed with the average around, it looks like to me around 30, it's right between 20 and 40. We don't see that many really below. It looks like 19, which, could potentially skew some of our results. So it's important to look at the data. And that's why I request you make a caption, because otherwise you might just plot the data and move on with your life. But really just taking a moment to look at it helps to frame the conversation, frame all the caveats. Because at the end of the day, it's not just the statistic you find, it's communicating it and having some type of decision based off of it. So in order to have that decision, you really need to know all of the caveats that are involved. So it's good enough, just one sentence. What do you see? Is there skew, or any clustering? Like, even I'm curious, what is this little pattern we see from, how young are they? But
those are the people trying to steal their credits from their kids or something like that.
Yeah, maybe. Yeah, I mean, yeah, depending, for the case study, maybe you'd want to investigate that further if you had some type of hunch. But yeah, exactly, maybe. But for the purpose of this, let's just create a new subset from the data frame for any time when the card equals no. So even just before we get to that, let's just see what is that distribution. So I'm just going to see how many people are no versus yes. So the majority of this sample do get the credit card approved, where a minority do not. But right now, our hypothesis is just looking at individuals who are rejected from the population. So now let's look at this standard deviation. And let's just see what that is. So we see the population standard deviation of this rejecting subset is about 10 years, 9.9. So let's take a random sample of 20 applicants. And we do this because we're testing our sample compared to the population. So this is just for demonstration purposes, assuming that this data set is exhaustive of the population we're trying to measure. But really in practical sense, that data frame is probably just a sample of a larger population. But we're going to do this just so we can show our null hypothesis compared against the population, which we assume is like our true population parameter. Is that okay? Does that make sense?
Yeah, I think it does. Only thing I was a little confused on was the create a subset for DF with application not accepted. So you basically just made it so that the reject pop equals when the DF doesn't equal when A equals card or something like that.
Thanks for taking a step back, because yeah, this is using Python to create a new data frame. And I appreciate it because I'm probably going a little fast here. This is taking the data frame from this column only when this column is equal to no. So similar to even on the midterm, when we were looking at just the college towns that were equal to Harvard University and creating a new subset from that, we're now applying that to create a new subset of a data frame only from the columns, or really just the rows where the card was equal to no. And that's why I wanted to see the value counts, because we're now excluding any row in this sample where card equaled yes.
Oh, okay. That now I get it.
Okay, and just to prove that this worked, if we're now, oops, the reason why that showed everything is because I didn't specify which column, and it just did all of them. But if I just wanted to see this column, just so we can prove. So DF was the entire data frame, and now I took a subset. And now if I looked at the same distribution of value counts for this new subset that I called reject pop, that's now 296. And I just did this for purposes of now I can work with this new subset, but we didn't really have to do this. I could have just used this, but really the reason I did this was so now we can work with just this pool of applicants who were not accepted, because the market analyst is only looking into this, not looking at who was accepted. But maybe even like if we were curious, we'd want to test the mean of folks who do get accepted, and then we would look at the other pool of samples. Did that answer your question?
Yeah.
Okay, cool. Perfect. So we are now taking a random sample from this. This is our sample compared to the population. And we're doing this so we can take that measurement and then compare it back to the population. So I'm just going to define my sample size of 20. And I use this random sampling, and I define my random state so that this is reproducible. And I'm only taking this from our subset we created of folks who were rejected from a credit card application. So we will calculate the sample mean, or our X bar, and the sample mean is just about 30. So just by looking at this sample mean, this is greater than our hypotheses value of 25. This casts doubt because it's greater than 25. But does this discrepancy, is this extreme enough to imply that we should reject the null hypothesis? What if this is just pure chance?
Right. I don't think it's big enough. I think like if it was like maybe 7 or 10 years, then I would say, but barely 5 is, not old enough.
You're right. And we can use statistics to bring your understanding, like your intuitive response, and bring that to a quantitative response. using our z-test to say, how far is this from the mean? And is it far enough that we can say it's statistically significant? But your hunch, I agree. It's not far away enough to say, that it's significant enough. But now we'll use what we just learned to actually prove that with statistics. So this is that z-test. I should have better documentation to say what's in this. So I'm just going to make a little, but this, we've seen this formula again. So we just plug in our sample mean, the mu that we're trying to test against, like the average, which was 25. So how far away is the average we found from the average we are testing for, divided by the population standard deviation and the square root of n. So I just broke that out, but that's the same formula from the slides. So now we have this z-score to show that this was 2 standard deviations away. But is this significant enough to say that there is reason to reject the null hypothesis and say that folks under 25 are more likely to get rejected? So this is our, I just wanted to visualize this, where we have our mean from the population, and we have the standard deviation of the population. And I just created a distribution along the x-axis to represent what that would look like. And we draw it. And this is now just getting a little bit more, we could have had all of this within the plot, and you've seen this all before. This is just breaking it down into 2 different steps and defining new variables, pretty much just to say, make a normal distribution out of all the values along our x-axis that are within 3 standard deviations above and below the mean. And that's what plots this blue line. And now what we're trying to find, if our value falls within this red zone, I made a new distribution to show the area that our value of 25, which is right here. So we would need our value to fall within this red zone for us to even have evidence to support rejecting the null hypothesis. And the value we found, let's see if we have enough evidence, even though it didn't even, what if it was just by chance? We need to prove that the value we had is not as extreme to support this alternative hypothesis. And you can use this survival function from the z-score that we just calculated up here to translate that back into the probability. This is the same exact thing of what we've seen before when you subtract from the cumulative density function of the z-score. So this value is exactly the same. And this is now the probability of seeing that value that we tested, our x bar. So we translated that from a z-score into a p-value. And we see that the probability of this value is 0.02. But we now need to compare that against our statistical significance to say, is this value extreme enough to state that it is even in this red zone? And is it past the red zone enough that we can consider this as evidence to reject the null hypothesis? So again, intuitively, Darren, you nailed it. Like this value wasn't even under the value we were testing for, so we wouldn't even expect it to be within this red zone. And using this p-value, we can now put apples to apples and compare this to our probability of actually seeing the null hypothesis being false. So in this case, we are using this p-value to say when the null hypothesis is true, and the null hypothesis being true of saying that the mean is going to be over 25, there's only a 2.21% chance that the sample mean will be 25 or less. So we're trying to now use our z-score to say, what is this area under the curve? And it's 2.21% chance or less, which is a small chance. And now we use our p-value against our alpha, and our p-value being what we just calculated, this brings it back to our type 1 and type 2 errors. If we decide to reject the null hypothesis, there is this 2.21% chance that our decision is erroneous. That we just got it due to chance, that there wasn't actually any relationship between someone being young, below 25, and being rejected from a credit card. What's the probability that we just made this rejection due to chance? And this probability gives us the statistics to put that into a quantitative value. But now we can even test this against our hypothesis and say, if the p-value that we found is less than or equal to this significance threshold of 0.05, we would fail to reject the null hypothesis, which would essentially be in accordance with the null hypothesis. But let me put this, because you'll see the language different. But it's all saying the same thing of either you fail to reject the null hypothesis, and it's a little convoluted, but it's important that it is in this language where we're not just saying this is true, this is false. It's more just saying we failed to reject the null hypothesis. We didn't find enough evidence to prove that this person is guilty, but there might be something we missed. So it's important that we have this nuance to the language we use, because science, we know nothing until we have evidence to prove something. And perhaps this evidence is erroneous. We need to be very specific with the language we use, essentially just to cover our tails, to use probability as probability, because there's still uncertainty inherent in everything that we're doing. So that's why this language is important to have nuance to it. And if our p-value is not greater than the threshold we defined, we didn't find enough evidence to reject the null hypothesis. So we failed to reject the null hypothesis. If the value is greater, if the p-value fell into here, we have evidence to reject the null hypothesis, and therefore we would have evidence for the alternative hypothesis. And we use this p-value to say the probability of having this just due to chance is so small that there's evidence to reject the null hypothesis. And so because our p-value here, just putting it here just so you could see, our p-value was not extreme enough to reject the null hypothesis, so therefore we fail to reject the null hypothesis.
Random question about Python. Is there an undo button? Like in all the other Google things?
Yeah, it gets, when you're in the cell itself.
Yeah.
Let me do plus test. This will give us an error because I'm trying to concatenate a string with an integer value. If you did Command Z while in the cell, which I just did now, you can have that same functionality. But if I did Command Z here, It's only by cell.
Got it. Okay. Thank you. Because I'd be like messing up. I'd be like, oh no, what did I put there? And now I know.
There is this
Oh,
where you can have more dexterity over what you undo, but it is pretty common with most like notebook environments. When you delete a cell, it's very hard to get it back.
got
So
it. So I won't delete
usually
anything.
I delete at the very end. And I usually, when I am working with things, I just give myself lots of space. Like I just make lots of cells and I give whatever I used to have below. And I kind of just work iteratively like that. And then I go and clean up my old stuff. So rather than deleting something, because you might find it was useful later on, I
Mhm.
usually just give myself lots of space and work and like take advantage of this almost like a sandbox type of environment. Like there's no reason to really delete anything due to like space constrictions.
Yeah.
So might as well just leave it until the very end when you just start cleaning everything up.
All right, cool. Thank you. I always wondered that. So glad you're able to clean it up for me.
Yeah, likewise. Yeah, and this also, kind of goes to show reproducible research. We can run this code again. We can share this with someone else, and using Python to have it in a notebook too. So we can do all this in R, and I assume the next statistics class in the program will use R, but a lot of these concepts, once you learn it, it's just translating it into another language and learning slightly different syntax. So there is a lot of overlap between using R and using Python. And I just know Python is used pretty ubiquitously in the industry, whereas I know R is actually more used in academia from what I've been exposed to. But usually most job applications also sometimes have R in addition to Python, but I know Python is very valuable right now. Okay, so bringing it back to our test, in this case, our sample data is actually in accordance with the null hypothesis, since the sample mean was 29, which is greater than 25. Therefore, there's not enough evidence to reject the null hypothesis. So, the world kind of exists as we thought. So in this case, back to the jelly beans, the world would exist without thinking jelly beans actually caused acne or fixed acne. So we didn't have enough evidence to reject the null hypothesis. So we kind of go back to, there was no discovery made. But this is also still important as far as like research goes, to show that there was no relationship. It's still very valid and important research, even if there wasn't a significant outcome that disproved our current understanding of the world. This just gets back to kind of incentive for publishing and discovery, where there really isn't enough research done on existing research to just prove something again. And just this brings back into like incentive, like there isn't enough incentive for us to have repeated research, because scientists want to discover new things, because that's where funding exists. And I just bring this up because we should be critical of everything. And now we have the tools to be more critical and say, okay, you found the significance level, but kind of let's unpack this further and really understand what this means. Okay, so let's walk through another example from the textbook. And I think that this is from one of the values we went through. This is something with back to school spending. I didn't list exactly which example this was from, so I will do that after class to make sure we have it from the textbook, just so you can reference when I just say example from textbook. Let me make it to do, because I would like to have the context of what the example was. So once we are finished with recording this, we will have more context, because all I have now is that it gives you the average of the population, the number of observations, and then the average from the sample, which is this X bar, and the population standard deviation, and then our significance level. So a lot of the homework questions will be very similar to this, where it just states what you need to have. But I had that other example from, a data frame in real life where you need to create these input parameters yourself. But at this point, we should be pretty familiar with an X bar being the sample, and we're comparing that against the population or whatever we're trying to prove against. So this is testing if the mean is different than this value. So we have this mean value of 606.4, which this is still just drawing the normal distribution based off of these input parameters of the mean and the standard deviation of the population. And we see this value being 606.4. And we're trying to test if the value from our sample of being 622 is far enough from this mean of 0, this mean of the population, to state that there's a significant difference. So in this case, this would be similar to the mean of the plant height from the hops testing, to say that the average is very different from here. So even if we had the average of 605, that's pretty close to this threshold of the mean we'd expect. But if we saw something all the way at 750, this is far enough from the mean to actually be in the tails to be considered extreme, that we wouldn't expect to see that value. But we set how extreme does this need to be using this significance threshold of 0.05. So this needs to be beyond 95% of the area under the curve for us to be considering this value extreme enough, and not just due to, kind of just how there's inherent variance in most things. So our sample statistic of X bar, we're now going to create a z-score of that. So we have this 62,600, which is probably somewhere around here. So intuitively, we might now know, since I plotted this, that this isn't really that far away from the mean. But we will use statistics to prove that, where we have it's actually just less than one, or it's greater than 1 standard deviation above the mean, given the population standard deviation. So we will now, yep.
Sorry. So that dotted line is the 6.06 or 606.40.
Yeah, that's a great point. I should have a legend here. Oh, actually, good point. Because this vertical line, great catch. This is actually the sample.
It looks a little further than 606. A little further.
Yeah, exactly. I'm very glad you're here. Okay, sample mean, and let's just show that, where we have the population mean. And let's make this one green and this one red. And I will make this just 1 dot. So now we can compare the difference. Excellent catch, because you're absolutely right. And that makes more sense anyway, because this distribution should be symmetrical around the mean too, because that's what this code is doing. So that makes a lot more sense.
So now the red line is probably the other one. What is it? 620 something? That's what it was.
Here, let me turn on the legend by plotting this. So I have labels here,
Yeah.
but I didn't have the legend show. And now instead of guessing, but yes, exactly. You were right. The red is the sample mean. And we have this z-score to say how many standard deviations from the mean is it. And if it was, so it's barely just one standard deviation from the mean. And if we wanted it to be extreme, it would need to be further away from the mean, like, because one standard deviation, that's most of the values here. Thank you for catching that. Any other questions about this?
No, that was the one.
Yeah, let's add axes here too. While we're improving the code I wrote here. Value of X, and I'll go back once I find the context around what the context is of what this X is. I assume it's probably some like monetary value. This might be even the example. I won't go back now, but I think it's one of the first ones that we talk through when it's a two-tailed test, because we're looking into the value either below or above this. It doesn't really matter. We just want to know, is the mean significantly different from the population that we would expect to see? And because this is two-sided, because we don't, this is not that less than or equal to, it's just not equal to, so we need to test it for both tails. We would use this in both sides. So we need to just multiply it by 2 to account for that. And again, this is equivalent to what we used before of the 1 minus CDF of this z-score, where this would be all of the area under the curve up until this value of the z, but we times this by 2 because we want that to be for both sides under the area. So when you're going through the homework, I would just stop for a second and think, what exactly are we calculating for? And I agree. I'm assuming that this might get a little convoluted because last time we didn't need to multiply it by 2, but that was because we had that error margin already divided by 2 beforehand. So now we're just using the same concepts, but in a different way. And because we didn't divide by 2 in the beginning, we now need to just multiply this by 2 in order to account for the area under the curve on both sides.
And we know we had to do it on both sides because it's equal to or not equal to with the null value and alternate.
Exactly. So in this case, we didn't care if the value was, greater than 750, similar to that last example when we cared, is the mean less than 25? Mm-hmm. In this case, we're just trying to prove that the mean is not equal to this value. So we need to account for both sides.
Got it.
So yes, yeah. When you want to work through kind of what's your decision tree that you should follow, exactly. Anytime we have a two-tailed test, we'll need to multiply this by 2. When we have the less than or equal to and greater than or equal to, we do not need to have the two-sided since we're just testing for one side. So we have this p-value, and just looking at this is a pretty large p-value because the probability of seeing a value at least as extreme as the z-score we saw, like this value of x bar, is pretty common, 16% chance that we would see just a value here because of where it is under the curve, or we would see a value because it's pretty common. It's not as extreme as what we saw before. So we can use the same, well, in this case, this would need to be, yes. So the p-value is greater than the alpha we established, which means that it wasn't as extreme as being 95% area under the curve, where that would be 0.05. in the tails. So, and it was very far away from that. So we failed to reject the null hypothesis. Okay, and this was something about back to school spending. So let me bring this back into here. Value of so this was something about back to school spending, and our p-value of 0.1657 is greater than our statistical significance threshold of 0.05. Therefore, we fail to reject the null hypothesis, or, you know, we do not reject. Let me just make the words more consistent. But again, those are all equivalent, saying we do not reject and we fail to reject our equivalent. So therefore, at this 5% significance level, we cannot conclude that average back to school spending differs from the mean. And therefore, the sample data do not support whatever this research analyst claim was.
Expensive.
Yes, and this just takes it a step further, thinking back to even when we were doing those control limits of something being within control and out of control. Like we can think of these upper bound and lower bound of where we would expect the mean spending to fall, and back to even that area under the curve. So let me just bring this back up here of just using now our probability to know kind of intuitively where we would expect. And this always happens in Markdown because it thinks the dollar sign is something else. So you just have to use this backward slash to say, hey, this is a dollar sign. Don't reformat it weird. So we would expect that the mean spending would actually be just within these intervals of being one standard. This was just calculating, you know, from one standard deviation, or this was the z-score for the 95% probability of what we'd expect to see. So the area under the curve there would really fall between here and here most of the time. And then anything that falls outside of that would have been evidence to support the alternative hypothesis. But this is kind of just saying, since our value fell between this confidence interval, we fail to reject the null hypothesis. So this is the same outcome as the p-value approach. It's just using it in a different lens. So just wanted to bring that up because that's why it's so important that we have these understandings of the area under the curve, because now we use it to either support or refute our null hypothesis. So the homework will be based off of all of this. I added some extra credit, which uses the population proportion. And that is based off of this case study. So let's say from what we went through the first one around this expenditure and default data, let's say a student is concerned that 80% of applicants will be approved for a credit card because of an annual income greater than 50,000. So as extra credit, you will state the null and alternative hypothesis confidence interval and go through these different evidence to claim or refute this. And that's similar to most of the other homework questions as well. But a little extra credit that is optional to do as well. Any questions?
No. How long is the homework going to be? Is it like 2 or 3 questions, like long questions like this, or is it going to be like a whole bunch of little ones?
Yeah, it's mostly little ones, a lot of just interpreting how to translate things into the null and hypothesis. Here, I can even, let me get it open. We can just walk through it quickly now. So a lot of it will just be constructing the null and alternative hypothesis from different scenarios. And this will be around, you know, should you use a 2-tailed, 1-tailed test defining consequences of the type 1 and type 2 errors that we talked about. So that's the, probability of a false positive and a false negative.
Mhm.
And then we will use where it actually defines it for you and defines all these inputs, where just using what we walked through right now to get them this to calculate the conclusion. And this should fall there too. The only one that gets a little more where we haven't talked about it explicitly was this population proportion. So that's from section 9.4. And so you'll just have to use a different formula for there. But the textbook has how to walk through this question in section 9.4.
Okay.
And there was one other extra credit that I added here because the textbook referenced this case study, and I found a chart, and I would like the class to give their critique on this chart and how they would want to improve it. Yeah.
Aren't like pie charts the devil?
Well, I wouldn't go that far, but yeah, how you would maybe itemize what is easy to interpret. But I appreciate that. Yeah, when I see pie charts, I do cringe, but not everyone is the same way, I'm sure, but for me, if you're representing less than 3 different slices of a pie, then really like you shouldn't be using a pie chart because it's difficult for you to interpret all these different angles for this area under the curve, especially it's a 3D pie chart, which anyway, I'll let the class determine their critiques, but I guess a little bit of a hint at some of my critiques. So I will stop sharing then and end the recording.